Recursion. It confuses novices. It's banned by NASA, and I can't stop thinking about it. How deep can it go? At this point, I believe I've set a world record for the deepest recursive function call, over 17 trillion nested invocations. It's literally the most profound thing I've ever done with a computer. To get there, I had to do a lot of crazy stuff like patching the kernel and writing a custom file system. Although, as I'll explain later, it was the open source contributions of ByteDance developers that helped me make the biggest breakthrough. I'll start at the beginning with the basic Python example. It takes just one line of Python to create a recursive bomb. This function can only call itself about 1,000 times before I get an error. The error is of course due to running out of memory in the call stack. Every time a function is called, the Python interpreter has to keep track of stuff like the parameters that were passed in, the line of code to return to in the calling function, and local variables. This, of course, uses memory. More and more memory for each function call until at some point you run out of memory and get an exception. You'll get various results with other programming languages. For example, I get about 50,000 recursions in JavaScript and 260,000 in C. Python has an API to increase the recursion limit, but eventually you reach a point where instead of recursion errors, the Python interpreter itself crashes due to running out of memory. I was able to get over 100 million recursions before crashing. In Linux, you can change the maximum amount of stack memory using the ulimit command. You can even specify unlimited stack memory. Of course, this isn't an infinite stack glitch. Just like the Python example, my recurse program gets killed by the kernel after a few minutes because the system runs out of memory. On my machine, unlimited stack, that gets me about 940 million recursions. C certainly appears to be more memory efficient than Python, but I was kind of hoping for billions of recursion. And so began my quest to set a world record. You can actually recurse forever if you compile the C code with optimizations enabled. But if you look at the disassembly, there's no function call here, it's just an infinite loop. The compiler has performed a tail call optimization to eliminate the recursion. Well, that's clearly cheating. We need to have some rules here. Okay, rule 1, I want real function calls using a stack. Tail calls don't count. To prove there's no shenanigans, you should be able to attach a debugger and inspect the call stack. I suppose if I'm making rules, I should start with the definition of recursion. Repeated cursing. Well, I certainly did a lot of that when working on this project, mostly at out-of-memory errors, especially when my editor was the casualty. And then there was the seg fault that didn't hit me until after 3 days of CPU time. That sucked. Where was I? Oh yeah, definition of recursion. Here's a serious definition from Wiktionary, the invocation of a procedure from within itself. I'd like to note that Python seems to have a looser definition of recursion. If you write 1,000 different functions that call each other in a chain, you'll still get a recursion error, even though no function called itself. Apparently, the Python developers assumed nobody would hit this limit without recursing. I'm actually going to take Python's relaxed view and say that recursion isn't strictly required. It's about the total number of nested calls, recursive or no. Really, this project is all about getting the most out of your memory, which means understanding virtual memory, physical memory, and file systems. And of course, using the stack efficiently. Let's talk about that. Before I go on, one last rule. I want my recursive function to actually calculate something. I started with the triangular numbers. These arise from arranging numbers into a triangle. They go 1, 3, 6, and so on. So you could just add n to get the next one, making for an easy recursive formula. Here's my C code to do exactly that. Note that there's a base case. The 0th triangular number is 0. This stops the recursion when you get to the end. I'm going to compile this in future examples with tail recursion suppressed, so it'll actually recurse. Now let's talk about what this code is doing at a lower level. Here's a stack trace showing a bunch of nested calls to my triangle function. This is nice for debugging the C, but it doesn't give you a picture of how it's using memory. So let's look at the disassembly. There are 2 places this function uses the stack. First, when it pushes a register to hold the value of n, and then the other place is with this call instruction. That pushes the address of the instruction where execution should resume when returning. Here's what the stack memory actually looks like. RSP is the stack pointer, and it holds the address at the top of the stack. That repeating address is what's pushed by the call triangle instruction. The other values correspond to the local value of n in each invocation. These are stored by that push instruction. You can see that each triangle function call is using up 16 bytes of stack. Let me show you the addresses of each of these stack values. The memory is shown as GDB would print it, but formatted into a single column. Each time a function is called, the next stack frame is placed at a lower memory address. The stack grows towards lower addresses on almost every architecture. Many people say this means the stack is growing down, but I think that's confusing, and it leads to upside-down diagrams. For example, this one on Wikipedia, where the top of the stack is drawn at the bottom of the diagram. Even Intel draws it this way. A baby knows that a stack grows up, not down. When we number things, we usually put the lower numbers at the top of the list. For example, the rows of a spreadsheet or lines of code. Or a memory dump in your debugger. Almost every debugger shows stack traces with the most recent call at the top of the screen. Except for Python, which does it upside down just to be different, I guess. So, unless you're a government researcher in Hawkins, Indiana, for consistency with almost every debugger in language, I urge you to turn those stack diagrams right side up and put the top of the stack at the top of the page. Okay, getting back to the triangle, it would be nice if it could use less stack memory per call. There's no getting rid of the return address, but what about the local variable? The way it's written, my triangle function has to remember the original value of n in order to calculate a result. But I can write it in a different way. I'll write my function with a second parameter to hold the accumulated result so far. These parameters can be passed as registers on AMD 64, so they don't need to be saved before recursing. Here's a stack memory dump of the new function. But wait a second, it's still using 16 bytes per frame. You can see the return address repeating every other row, but the other rows look like uninitialized junk. So what's going on? If you look at the disassembly, you'll see that the compiler is subtracting 8 from the stack pointer but doesn't use the memory for anything. The reason is that the compiler is following the System 5 ABI, which requires the stack to be 16-byte aligned for compatibility with vector instructions. Well, that's another compiler switch we can use. I won't be using any vector instructions in my code nor calling into any libraries, so this is safe to do. Actually, at this point, I just started writing code in assembly. This gave me total control and let me use registers more efficiently. Here's my stack now, just return addresses. So I've doubled my recursion. At this point, it doesn't seem like I can make the stack any denser without violating my rules. Actually, stay tuned for more on that. But right now, I'd like to talk about my memory problem. I can't recurse anymore because I'm running out of memory. I'm doing this on an Intel NUC that's only got 16 gigs of RAM. I could buy more, but that's pretty expensive, and the CPU only supports up to 32 gigs anyway. It would be more realistic to increase my swap partition size. My disk is only 500 gigs, so maybe I could upgrade that. So here's a question. If money were no object, and I could buy all the memory I wanted, what's the theoretical maximum possible call stack size? To answer that, we have to talk about how memory is laid out in a process. The call stack is just one area of virtual memory in a process's address space. Other regions include the heap and code. Here I'm showing a simplified diagram of a 32-bit process. 32-bit addresses, of course, exist in a 4 GB memory space. Traditionally, addresses up to 3 GB are available to user mode, and the rest is reserved for the kernel. As a program uses more stack memory, the stack grows towards lower addresses, as we discussed. Meanwhile, the heap is growing towards higher addresses. This layout gives flexibility to programs that have different memory needs. Now let's take a look at the 64-bit memory layout. I'm also going to show some more memory regions, such as shared libraries and thread stacks. This is still very simplified and not to scale. You can see all the memory regions of a process by inspecting the procpid maps file. Another thing to note is that not every 64-bit number is a valid memory address. In my examples so far, the addresses have all had a lot of leading zeros. That's because the highest possible user mode address of my CPU is 7, well, that number with a bunch of Fs, making the total address space 128 terabytes in size. You won't see a pointer with junk in the high bits, except for kernel addresses, which must have all ones in the high bits. This results in a gap between the maximum valid user mode address and the minimum valid kernel mode address. It's an architectural no man's land, and it's humongous. If we tried to draw it to scale, the gap would dominate everything. Getting back to the 128 terabytes, that's the theoretical maximum stack size. Assuming that I could just find a way to move, shrink, or eliminate all those other mappings to make room for just a gigantic stack. As for upgrading my NUC, well, it would be fun to provision a system with 128 terabytes. But let's think again about the data that's on the stack. It's just the same return address millions and millions of times over and over again. That's obviously highly compressible. So I shouldn't need to buy more memory to do this. Instead, I should be trying to get more out of what I already have somehow. So I briefly investigated a few off-the-shelf options for compression, but I wasn't too optimistic that anything was going to be able to achieve my desired compression ratio. I need to have like almost zero overhead to do this. For example, ZSwap, if I'm reading this code correctly, allocates a non-trivial structure for every page of memory that it compresses. So maybe one of these features or something else would have worked for me out of the box. I confess I only made half-assed attempts with the first two, and I didn't even try Btrfs. The truth is, I had been looking for a long time for an excuse to mess around with file systems in user space, or Fuse, and this problem seemed like the perfect opportunity. You may be asking, what do file systems have to do with the stack? Let's go back to the memory maps. That word maps is an important term. Each of these regions is a mapping that connects memory addresses to some corresponding data, which might be in physical memory or in a file on disk. What if I used a file for my stack? The cool thing about file maps is that you can map a file that's way larger than the RAM that you have. The kernel will only fetch data from the file system as needed, and it only has to keep part of the file contents in memory at a time. And what's a file system? Well, it's just an API for accessing data. Some file systems work on disks, others don't. For example, a file could be on a remote server, or even generated on demand, like in the case of /proc. Fuse lets you write your very own file system without having to do kernel development. All you have to do is implement some callback functions to perform operations like reading and writing to the file. So I made a custom minimal file system. It has a root directory containing a single file named stack, and it's 128 terabytes in size, because I said so in my callback function. So my idea is that we'll map that file as the stack of my recursing process using the mmap system call. The Fuse program, that runs in a separate process and handles the I/O requests. Behind the scenes, the kernel will still be managing my stack memory using the page cache. Only a small part of the 128 terabytes are going to fit into physical memory at a time. The CPU's paging hardware handles the translation between virtual and physical addresses. If this were typical stack memory that wasn't backed by a file, then it could be swapped, but instead, it's going to be handled by my Fuse program. So my program has to implement a way to read and write this pseudo stack file. And what about what's the contents of the file? Well, that's just zillions of copies of the same return address over and over again. So my Fuse program remembers only 4096 bytes of actual data at the very end of the file. Whatever is written here, I can mirror that to all the other positions in the file when I implement my read callback function. One detail, I keep track of the minimum write offset so far. Any reads at offsets before that are answered with zeros to be consistent with a normal stack. Let's look at it vertically to see it. As data is written to the stack, that minimum offset decreases and the zeros are replaced with the mirrored data. Again, remember, this picture shows the apparent contents of the file is implemented by my Fuse read callback. Here's what that looks like in pseudocode. My actual code is a lot messier than this. You can see the only memory I need is for that one page of data that actually exists. And here's the gist of the write callback function. I simply ignore writes to anything that's not the last page. So this file system scheme doesn't support arbitrary data. It's really just a proof of concept. I could have added code here to check if the data doesn't match what I expect to see, but for this project, I know it's always going to be those return addresses. One corner case, what if the recursion is only filled part of a page, like RSP's in the middle of the page, and it gets written back? Well, then the first part would be zeros and the last part will be return addresses. The thing to remember is we're not directly accessing the Fuse file system. Instead, we're reading and writing to a page in the page cache. The kernel considers the cached version of the page to be current and correct. It's not going to replace it with older data from the file. In fact, when our program modifies the page, it gets flagged as dirty, and it's eventually written back to the file via Fuse. So yes, we could theoretically see a Fuse write of a half-filled page, but since my program is very quickly recursing, it would soon be followed by a completely filled page. Long story short, this is obviously very far from enterprise quality code, but nevertheless, my recursing program sees memory in a consistent state, so it works. So back to the question of how to map a file that large into my process. What about all those other mappings that are in the way? Well, the mmap system call will happily and silently replace existing mappings if you provide the map fixed flag. You can set almost whatever address and length you want. You know it's going to be fun when the man page tells you to be careful. Well, there are a couple of restrictions. You're not allowed to map the very last page on x86. That's because Linux is avoiding some CPU corner cases. Oh well, it's only 4,000 bytes. You're also not allowed to map the very first 64K of memory. The kernel's trying to make sure that if you dereference a null pointer that there won't be anything there. This one is an easy fix. You can set the minimum address to 0 by writing to a file in /proc. So now I can write code like this and it won't crash. Like, here's a full example program. I can compile and run it, and it safely modifies and prints data located at address 0. I've just turned C into a memory-safe language. Okay, not really. Doing this made my code harder to debug. So I actually put an interrupt instruction at address 0 to force a crash if my code ever jumps there. Okay, so here's my virtual memory plan. I'm going to write my recursive code in assembly and put it at the very beginning of the address space. I'm going to use the rest of the address space for my fuse stack. The stack pointer is going to start at the highest possible address, and then as we recurse, it's going to eventually reach the end of my code. I also considered putting the code at the end of memory and the stack on top. I didn't have a particular reason to favor one layout over the other, but putting the code at the start ended up being a lucky choice because it allowed me to get another 500 million recursions later on. Placing my code at address 0, that was kind of annoying. I ended up writing a linker script to do that. I could have used mmap and memcopy, but the linker script let me keep my debugging symbols intact. You're probably wondering about how my program can be stable if I just obliterate all this other memory. My recursive function doesn't need libc or any other library code. It doesn't have multiple threads, and it doesn't need the heap. I did a bunch of stuff to avoid glibc nuisances, most notably not building against it. Most of this was probably unnecessary once I started using a linker script. I have some more bootstrap code that sets everything up. Here's the part that opens the fuse stack file and mmaps it. I had fun writing a giant constant into the stack pointer. The last thing the setup does is jump into my recursive code. And here's the recursive code. This gets mapped starting at address 0 at the very beginning of memory. Here's that interrupt I already talked about. Next, I have my recursive function. I decided not to use triangular numbers after all because the 17th trillionth triangular number is too big to fit into a 64-bit register. So instead, I'm just recursively multiplying a number by 2. The setup code calls into an outer function which wraps the recursion and exits cleanly at the end using the calculated value as the exit status. Only a few lower bits of this actually make it through, but it's usable as a sanity check. My recursive code is less than 32 bytes and the setup is only about 100 bytes. But the loader works in pages, so there's some empty space afterwards. The bootstrap has to map the fuse stack starting at the next page at 1000 hex. Normally code mappings should be read-only, but my linker script makes it writable so that I can get a few hundred more recursions by overwriting that bootstrap. So I got this working and started recursing. Here's what the /procpid maps file looked like with the two maps. You can see that there's a third mapping from the kernel address space, which is used to accelerate some system calls, but that's not relevant to my program. Things were looking really good at first, and I was getting billions and billions of recursion, way more than I could before. But it soon became apparent that I had a problem. The system was using more and more memory. Curiously, the recursion process itself was using less and less memory, at least as Top reported it. Within a couple of hours, the system started to thrash, and then came the inevitable out-of-memory crash. The explanation is in that giant number in the kernel log. It's the amount of RAM that's being used for page tables. Remember this diagram? I had kind of waved my hands about those page tables. They, of course, take up memory too. The overhead is pretty small, only about 0.2%. The kernel creates those page tables on demand, but it's not removing them after the corresponding physical pages are flushed from the page cache. This isn't a problem for normal applications, but 128 terabytes of stack That would require over 256 gigabytes of page tables. Oof. I needed to find a way to deal with this. So I did what anybody would do that's looking for stackmaxxing advice. I went straight to TikTok. For it was a ByteDance developer who made a recent commit to the kernel that allows me to clear out those page tables manually. So I have to wonder, does the famous TikTok algorithm do a lot of recursion? This is the magic system call. I can use madvise to instruct the kernel to free the page tables associated with stack memory that I don't need for a while. Unfortunately, this is going to be a pain to do because it has to go into my recursion code, which I'm writing in assembly. So in assembly, I'm going to have to calculate the address range and then make a system call. That's going to add dozens of bytes to my code and take away from number of recursions that I can make. But wait, in Linux 5.10, there's a system call that lets you madvise another process. Although it doesn't support the TikTok flag. I wonder why. Well, I found the kernel function that checks the flags, and, well, what the heck? I'm just going to change it and see what happens. And while I'm at it, I don't see why I shouldn't be able to mmap that last page of user mode address space either. So I updated my Fuse program to call process madvise periodically to clear those page tables. It's aware of the offsets of where it reads and writes are happening, and so therefore it has a good idea where the current stack pointer is in the recursing process. At this point, I came up with one more idea about how to get more recursions. Remember how each stack frame is 8 bytes? That's because that's the size of a 64-bit address. In a 32-bit process, I could have a 4-byte stack frame. The problem is a 32-bit process only has a 4 gigabyte maximum theoretical stack size. But on x86, we can actually have it both ways. You can switch the CPU between 32 and 64-bit mode, and that's exactly what I did. Here's what my code looks like. I've added a check to see when we've reached that 4 gigabyte threshold on the stack. Then I use an obscure instruction to make a far call to enter 32-bit mode where I recurse some more. When I'm done, I use another obscure far return instruction to get back to 64-bit mode. This little trick gained me about 500 million recursions at the cost of a few dozen bytes of code. Here's how it looks when it runs. There are zillions of copies of the address hex 12. That's the return address from my call instruction. Remember, I'm mapping it in the first page. Eventually, we reach the 4 gigabyte threshold and we're ready to cross into 32-bit mode. Then we far call into the 32-bit code segment. The far call pushes a 32-bit return address and also a 32-bit code segment selector value. From now on, a call instruction pushes a 4-byte return address onto the stack instead of 8 bytes. Then we keep recursing more in 32-bit mode. So obviously, the stack memory for 32-bit mode contains different data than the 64-bit stack. So my Fuse file system doesn't work for that. So I just made a normal memory map for this region. I can spare the 4 gigabytes of RAM. Also note that a 32-bit return address only supports code that exists inside a 32-bit address space. So this wouldn't have worked if I had put my code at the other end of memory outside the 32-bit address space. So I had made a lucky choice earlier on, as I said. So I kicked off what I hoped was going to be my world record run. Did I mention how slow this is? My poor little nut got really hot and the fan was screaming. At least it kept my coffee warm. Hours in and my memory usage was stable. My madvise changes were working. Well, there was this one glitch. My kernel log is getting spammed with these scary warnings. Maybe that's why there's a restriction on using that madvise flag across processes. But hey, at least it's not panicking. In fact, my code was stable for 3 days of recursing, at which point it finally reached the 32-bit code where I had set a breakpoint in the debugger, and it crashed. I was so annoyed, I rage quit and I botched the screenshot. Here's what I think happened. I intended to set my breakpoint on the destination address of this far call instruction. The way GDB prints it, it looks like the destination is that symbol stub32. But stub32 isn't the function, it's the address of the function. So when GDB set the breakpoint, it wrote an interrupt opcode into that address, corrupting it, and causing the call to jump to the wrong place and crash. Well, that was frustrating. But the good news was that I'd recursed over 17 trillion times, though I didn't reach the end of memory and it didn't return. Time to kick off another run. This time, I'm using hard-coded breakpoints only. And after another 3 very long days of recursing, I reached the end. 17,592,722,915,310 recursions. As far as I know, nobody has recursed this far before. So here I am at the breakpoint I'd set for that final frame of recursion. The stack pointer is at hex 40, which is just beyond the last instructions of my assembly code. One more function call and it would have started corrupting that code. Okay, I'm going to dump the stack memory here. Those hex 30s are return addresses inside my recurse32 function, as you can see. At the other end of memory are the 64-bit return addresses, which keep going until we get to the 128 terabyte end of the address space. To get GDB to display a more traditional stack trace, I had to continue back to the 64-bit code. As you can see, it's scrolling pretty slowly. It would take GDB centuries to print the entire stack trace. The next question, could I return back? That should be a rule. This went a little bit faster, 2.5 days, and my final breakpoint hit right before the outer function was going to call sysexit. As you can see, RSP is now all the way back to 128 terabytes. And RDI holds the value of 35 trillion and change, which is exactly the number of recursions times 2. So my recursive doubling functions did the right thing. Let's continue. And it safely exits. Okay, I think that's just about enough recursion for me. And for my NULL. Just listen to it now. But if you want to break my record, I've got a couple of ideas to share. You could surely eke out some more stack frames by trying to shrink the assembly code. For example, the hardware interrupt instructions, those are unnecessary. I actually used a couple of tricks in production that I didn't show yet to make the code easier to read. For example, I called a function via register to save a couple of bytes. But code golf is playing for peanuts. You could actually recurse 512 times as far as I did with newer hardware. The 128 terabyte address space, that's a consequence of my CPU's 4-level page table scheme. New hardware supports 5-level paging, giving you 64 petabytes of address space. So you could reach quadrillions of stack frames. As is, my code would take like years to get that far. You definitely want to do some serious optimization. Fuse, probably not the way to go. The final frontier is for you OS dev folks. I was talking earlier about the giant gap between user and kernel mode address space, but that's unsigned pointer thinking. If your stack pointer were to reach 0 and keep decrementing, you'd end up with a kernel mode address, but you could think of them as negative addresses. So let's rearrange the diagram to show it. If you're writing your own operating system, there's no rule that says you have to allocate half the address space for the kernel. You could dedicate most of it to recursion and have a stack of almost 128 petabytes, which could accommodate 18 quadrillion stack frames. The challenge for you is to figure out how to actually implement that. I look forward to hearing about future research into this very important topic. I congratulate you on reaching the end of this video. I'll see you next time, I hope.